A mysterious creature appeared in front of you and asked you to prove that there are infinitely many primes, or he will eat you. Will you be able to do it? This is a classical example of proof by contradiction. Proof by contradiction is a consequence of two axioms in logic. The first of them is the law of excluded middle. It states that for each proposition, it is either true or false. This means a statement can't be true and false. Also, if it's not false, it's true. The second law is the law of non-contradiction. It states that contradictory propositions cannot both be true in the same sense at the same time. To illustrate this better, consider these two statements by Alice. She states she was in America yesterday at 6 p.m. Then she also states that she was in Australia at 6 p.m. That's a contradiction. Contradictions can't exist. And we have to resolve this. She was in America or Australia, or neither. But what's important is that both of the statements can't be true in the same time. Here's the setup for a proof by contradiction. Premise 1. The law of excluded middle holds true, and the law of non-contradiction holds true. Premise 2. For a proposition Q that you want to prove is true, assume it is not true. Premise 3. Show that if Q is not true, a contradiction arises. Premise 4. Thus Q cannot be false. And if a statement is not false, it must be true. Conclusion. Therefore, Q must be true. This is how every proof by contradiction goes. I encourage you to pause and ponder this, as we will use this method to prove that there are infinitely many primes. So we can start by assuming that there are finitely many primes. Therefore, there exists a starting prime P1 and an ending prime Pn. Consider the number Q defined as the product of all the primes plus 1. Q is greater than 1 and not divisible by any of the primes. This statement is true because by adding 1, every modulus has a remainder of 1. Therefore, Q must be either a prime itself or have a prime factor not in the list. In both cases, it's a contradiction, but I want to be more rigorous than this. Let pk be a prime factor of Q. We are continuing on the assumption that Q is a composite number that is composed of the list of primes we started with. Given that Q minus the product of all the primes is 1. Since pk divides Q, it must also divide Q minus the product of the primes. Therefore, pk must divide 1. Yes, the smallest prime number is 2. 1 over 2 is 1/2. And that doesn't belong with the integers. This contradiction implies that our initial assumption that there are only finitely many primes is false. This proof that I just showed you provides concrete evidence for the infinite number of primes that exist. It was written and constructed by Euclid. Euclid is an ancient mathematician who lived around 300 BC and is regarded as the father of geometry.